Welcome everyone. Today we will explore linear regression, which is a foundational concept in machine learning. Our main objective is to understand how we can mathematically describe and find the best possible straight line that represents the relationship within a set of data. This involves taking a collection of input features and trying to predict a continuous target variable. To accomplish this, we need a way to measure how well our line fits the data. This brings us to the idea of an objective function, or loss function, which quantifies the error between our model's predictions and the actual true values. The entire process of training a model is essentially a search for the best model parameters, in this case a weight and a bias, that make this error as small as possible. By understanding this process, we learn to frame machine learning as a problem of optimization. When we try to minimize our objective function, we often speak of a loss surface. You can imagine this as a landscape where the elevation at any point is determined by the error for a specific set of model parameters. Our goal is to find the lowest point in this entire landscape. However, the landscape can be complex, containing many valleys. We must distinguish between a local minimum, which is the bottom of a smaller valley, and the global minimum, which is the absolute lowest point anywhere on the map. Standard optimization methods can sometimes get trapped in a local minimum, leading to a good but not the best possible solution. This is why global minimization techniques are so important. They are designed specifically to explore the whole search space and avoid getting stuck, with the goal of finding that one true global minimum. In contrast to searching the entire landscape, a very common approach in machine learning is local minimization, with gradient descent being the most famous algorithm. Imagine you are on a foggy hill and want to find the bottom. The best strategy is to feel the ground for the steepest downward slope and take a step in that direction. This is precisely how gradient descent works. It calculates the gradient of the loss function, which tells us the direction of steepest descent, and then updates the model parameters by moving in the exact opposite direction. This process is made efficient by an algorithm called backward propagation, or backpropagation, which computes the necessary gradients for all the model's weights and biases. While gradient descent and its variance are powerful, their reliance on local information means they can sometimes get stuck in a local minimum or a flat plateau, which is a key limitation to keep in mind. Now, let us apply these ideas directly to our linear regression problem. While global techniques are an option, linear regression is often simple enough that we can rely on more direct methods like gradient descent. The process works by iteratively updating our weight and bias parameters. The new weight is calculated by taking the old weight and subtracting the partial derivative of the error with respect to the weight, scaled by a small learning rate. We do the exact same thing for the bias. This vector of partial derivatives, called the gradient, points in the direction of the steepest increase in error, so by moving in the opposite direction, we steadily walk downhill on the loss surface towards a minimum. Even though this method is highly efficient for linear regression, the value of global minimization becomes much clearer when we face more complex, nonlinear problems where many local minima exist. This first piece of code demonstrates how to solve our linear regression problem using a global minimization technique. First, we use the NumPy library to generate some synthetic data. We create a set of input values, x, and corresponding output values, y, that follow a linear trend but include some random noise to make the problem more realistic. Next, we define a Python function to calculate the mean squared error, which will serve as our objective function. The core of this example is the call to the differential evolution function from the SciPy library. We tell this function to minimize our error function by searching for the best weight and bias within a specified range. This algorithm intelligently explores the entire search space to find the parameters that produce the lowest possible error, giving us a globally optimal solution. To offer a comparison, we will now solve the same problem using the more common gradient descent method. The code defines a function that implements this local optimization algorithm. It requires the data, an initial guess for the weight and bias, a learning rate to control the step size, and the total number of iterations to perform. Inside a loop, the function repeatedly calculates the model's predictions, computes the gradients of the error with respect to the weight and bias, and then updates the parameters by taking a small step in the direction that most reduces the error. After running this loop 1,000 times, we print the final optimized parameters. This will allow us to directly compare the result of this iterative, local approach with the result from the global search method we used previously. Visualizing our results is a critical step to building intuition and verifying our work. This code uses the matplotlib library to create a plot that tells the whole story. First, it creates a scatter plot of our original X and Y data, which appears as a cloud of points with a clear, linear trend. Then, we overlay two different lines of best fit onto this plot. One line is drawn using the parameters we found with the Global Differential Evolution Optimizer. The other line is drawn using the parameters we found with our own gradient descent function. As you can clearly see, the two lines are practically on top of each other, cutting perfectly through the data. This provides strong visual evidence that for this problem, both the global and local optimization methods successfully converged to the same excellent solution. The true value of training a model is its ability to make predictions on new, unseen data. This final piece of code demonstrates this predictive power. We take the optimized weight and bias that we learned from our training process. Then, we invent a new input value, called a query point, that the model has never seen before. We feed this new input into our linear model equation, along with the learned parameters to produce a corresponding predicted output. The code then generates our familiar plot of the data and the fitted line. But this time it also adds a special marker showing the exact location of our new query point and its predictions. This illustrates the ultimate goal of our work, which is to generalize from the data we have seen to make educated guesses about data we have not. To summarize our journey, we started by defining linear regression as an optimization task. The core challenge was to find the best line that fits our data, which we translated into finding the model parameters that minimize an error function. We explored the conceptual landscape of this function and contrasted two primary strategies for finding its lowest point. Global minimization techniques, like differential evolution, are built to search the entire parameter space to find the single best solution. In contrast, local techniques, such as the very common gradient descent algorithm, start at a guess and take iterative steps down the steepest slope. Through our code examples, we confirmed that for a straightforward problem like linear regression, both strategies guided us to the same optimal model, which we could then use to make accurate predictions on new data.